Awesome. All right. Good morning, everyone. My name is Eddy Jimenez, and I'm a biomedical engineering senior at San Jose State University.
Hello, my name is Jonathan. I'm also a biomedical engineering senior at San Jose State University.
I'm Kevin. I'm a biomedical engineering senior at San Jose State University.
I'm Hyunju, biomedical engineering senior here at San Jose State University.
And we are the flexible 3D printed infant hand. So just to give you a quick overview of the contents, we're going to talk about the background behind our device, the motivation behind it, the FDA considerations, as well as all the testing and methods we try to do throughout the whole semester, the whole school year, as well as our experiments, all the results we obtain, and of course, we're going to talk about the results in order to provide future work, or to think about the future work. So a really quick background overview, we are focusing on transversal limb deficiency. As you can see right here, we have a picture of a baby with achyuria, which means they're missing their hands. This is due to congenital limb deficiencies. So unlike adults who usually end up with accidents where they have to have their limbs amputated, thus they need a prosthetic device. Infants, or some of the infants in the United States are born without a limb. In this case, they're born without the hand, or sometimes they're born without the forearm and the hand as well, right? According to the research we've done thus far, we do need to look for prosthetic devices for kids who, around 3 months is the optimal time to provide a kid with an infant hand, with a prosthetic device, right? So as I talked about before, achyuria is for kids who are missing just the hand itself, while incomplete hemimelia is for both forearm and hand deficiencies, right? So question is, what type of prosthetic device do you want to provide infants at such a young age? Well, as you guys probably know by now, there are 3 main types of prosthetic designs. There's body-powered, myoelectric, and passive, right? So as you can see in this upper picture right here, a myoelectric prosthesis, the way they work is to take advantage of the action potentials sent out by the somatic system, right? So all the muscle contractions that you usually do with your arms, there are electrodes that are attached to your residual limb, and they detect all muscle contractions, thus providing the movement with the myoelectric prosthesis. Myoelectric prosthesis can do either basic movements such as wrist extension flexion, and it can also do complex finger articulation as well, so for bilateral, unilateral grasping, right? On the other hand, you have a body-powered prosthesis, where, as the name implies, it takes advantage of the muscles or the movements that you make with your natural shoulder muscles, and through a cable system, you can actually move the body-powered prosthesis around. This one is a bit more basic as compared to myoelectric prosthesis, but it does the job well in performing daily activities of living. So prosthetics are basically needed to avoid overuse and injury, right? So you have someone who's missing a limb, and you don't want them to overexert themselves with their natural limb, because over time they just tend to hurt themselves, right? Proper growth and development, you want to make sure when someone grows up they have proper symmetrical growth, right? You don't want to have one part a little bit bigger and the other one kind of small, right? That's injury. That's where injury occurs. Self-image as well, especially for kids who are really, really young. It's really it's best to usually provide them with a prosthetic device, so that way they integrate this device as part of their own system, right? Part of their own limbs, part of their own hands. Otherwise, if you try to, let's say for example, provide them a prosthetic hand like at 1 or 3 years old, there's a high chance you're just going to take it off. They're just going to pop it off since they're so used to moving around with their natural limbs without really thinking about the residual limbs as well, right? So, question is, which prosthetic device is best? Well, the problem with kids is, especially at such a young age, they tend to grow rapidly. Every 3 to 4 months, you need to replace the prosthetic itself. So you provide them with a myoelectric prosthetic or a body-powered prosthesis. Guess what? Your kid's already grown up, so you need to replace the hand, which can be pretty expensive. Kids also tend to be kind of destructive too, so as they interact with their environment, as they're walking around, exploring, putting their hands in their mouths, right? You basically provide them a good chance of destroying the prosthetic device itself. Right? On the other hand as well, you want to make sure that the kid can use the device due to the fact that the kid is so young that their developmental capabilities is still pretty limited, right? So if you ever see an infant play around the environment, they're usually like flinging their arms around. They have no real sense of control, especially when it comes to complex finger or digit movement. So you want something really basic. You want something that works well, that's affordable, that's looks good, but at the same time is functional to at least provide some type or at least a basic activities of daily living. So we focus on the passive prosthesis, right? Unfortunately, due to the fact that there's like a small number of kids born in the United States with congenital limb deficiencies, in this case 1,500 per year, the market tends to be really limited. So as you can see right here on the left-hand side, we have the Greek series hand, right? It looks good. If you see one in real life, it looks almost like it was like actual baby's hand. Problem with that, it tends to be really limited in terms of functionality. They tend to be really cup-shaped, and they do provide some sense of movement, but really not that much functionality. Or you can have hands such as a child at the prehensors from TRS Inc. Right? These hands can be pretty functional. You can interact with the environment, but as you can see from the image, they look really robotic, really claw-like, right? And that's not exactly something as a parent that you want your child to wear. So based on the previous team, in this case the team from the University of Toronto, they actually came up with a design for passive prosthesis that attempted to answer both functionality and cosmetic appearance. When it came to benchtop testing and the design, it did work. Problem with that, as not only is a PVC glove too, but the inside the stainless steel wire skeletal, the skeletal system, I guess in this case, proved to be really poor in terms of durability. So after 40 cycles of just like bending the hand, of using it, the wires on the inside tend to break, right? And of course, with a high cost, due to the fact that they used a PVC glove to attempt to answer cosmetic appearance, they actually provide to be like 90% of the total cost of making a hand, right? So what's our objective? Well, the team at the University of Toronto had a really good idea in terms of functionality and cosmetic appearance. So we're still attempting to answer those factors with our design as well. We still try to aim for lifelike appearance. We're still trying to aim for at least some type of functionality in terms of basic activities of daily living, right? You want the kid to be able to walk around, crawl around, be able to interact with the environment, and at the same time not worry about, like putting their device inside their mouths, right, just drooling all over it. At the same time, we hope to, or in this case, aim to increase the durability by replacing the stainless steel wire with nickel titanium alloy.
So for FDA considerations, our device is considered as class 2 device because our device is not implanted. It's just fitted externally. So we thought this would be classified to class 2, which requires 510K clearance. And we searched a protocol which is possible for our device, and we found out IRA is best for our device, which is hand and external limb component. And we found two devices which are substantially equivalent. And they both have same intended use as ours. They do not use same technology as we use, but our new technology does not make any effectiveness or safety issues. So we kept going on that, and clinical testings are not required as this is 510K clearance, but we did some benchtop testings to show that our device is at least effective and safe as other devices. So the two main materials we use are nickel titanium alloy, which goes to inside the hand and works as a skeletal system, and the other one is Filaflex, which will be the surface of the outer material of the hand. And nickel titanium, we chose this because the previous team, they used stainless steel, and they, as Eddy mentioned, it failed after 40 cycles because of strain hardening, which makes the material hard, but it makes the material, it reduces the ductility of the material, so it breaks easily after repeated bending. So we use nickel titanium. This has shape memory alloy. This is shape memory alloy. It's more durable than stainless steel, and we chose 0.03 diameter wire. And we chose Filaflex for our material for printing, and there are not much material available to print 3D printing as something like rubber, flexible material. We choose 80 to 80 hardness. It's harder than tire, but it's softer than shoe heel. This is there were some other material we can choose, something like Ninja Flex, that is 85 A hardness, which is harder than ours, which is stiffer than ours, so it might not flexible as ours. So we choose Filoflex, and this is also biocompatible. It's not non-toxic, and no skin or mucosal irritation occurred through the material.
So this is our design of experiments, and most of the variables ended up being related to our 3D printing portion. So we had options to choose different infill patterns, which is the material inside the hand. There's going to be a certain number of perimeters on the top and the sides that are printed, and all the space within will just be printed with a specific pattern. In this case, we could choose to have 20 to 30% of that space filled, and also choose different patterns, which would be cubic, concentric, or rectilinear, and these are just the pattern of lines within. We also had options of choosing the layer height. This will change the accuracy of the print, essentially, because you're going to be printing more layers that are smaller. And also notch configurations and print orientations are related to the bending and also the actual print. The previous team used horizontal because we need to insert the nickel titanium wires within the hand itself. And this is very difficult to do for the vertical orientation. Can you go back about 2 slides? One more. Sorry, just one more. You can see in their design they had like a looped design to join these 2 fingers, and that was not really feasible to do if you printed vertically, because you would have to insert it from here or insert it mid-print, which would collide into the print head. So they chose to print horizontally and insert the wires mid-print. Okay.
All right. As for our methods of achieving the objectives outlined earlier, we split it up into 3 sections. One section being for the nickel titanium alloy wire. For that, we underwent some manual bending testing to prove that the wire would be more durable and have a longer product life than the previously used stainless steel wires. And we also went through a few different processes in order to make an annealed internal wire frame, which we'll get into a little bit during this presentation. For the Filoflex outer material, a lot of testing had already been done by the previous group in order to assert that that was the optimal material to use for this project. One thing that we wanted to add on was observing the level of deterioration of the Filoflex during one of the use cases, which we will expand upon in this presentation as well. And then for bringing it all together with the hand, we went through 3D modeling, 3D printing, transformation, tensile, and compression testing in order to assert the effectiveness and durability of the device.
So for the bending test, this is the first test we did, and we did this test because the previous team's wire breaks after 40 cycles. So we measured how many cycles the nickel titanium alloy will stand over. So we did manual bending, and we set the test criteria as 9,000 cycles because we said 100 cycles are made per day, and 3 months of use is 9,000 cycles. Because babies not really bend their fingers, and as parents helps the baby to bend or stretch their hands, so 100 cycle overshoots whatever is made in reality. And material we used was 0.03 as mentioned, and counting method we had 1 cycle per second, so it counted 2 hours. So we didn't actually count it, but we counted the time we bended the wires. So for the result, all the 3 samples passed the test. So we can say the nickel titanium is it can replace the stainless steel wire that was used in previous design.
Okay, so for the interior wireframe, what we want to do is basically shape the nickel titanium alloys to resemble a simplified version of a kid's skeletal structure, right? In this case, a hand. So what we did right here, we took the alloy wires, we shaped them as best as we could and to resemble a hand. Then we affixed them in this custom-made board right here, as you can see, all of it's stainless steel. Once we did that, we basically set it to this furnace here at the first floor of the engineering building. We set the furnace to 500 degrees Celsius for approximately 10 to 12 minutes. And we did that because it's around that time and around that temperature that the nickel titanium alloys tend to be trained, right? They tend to take to this shape as well. So once we took them out and we immediately quenched them in icicle wire, what we can do from right here, let's say for example I have a wire, deform it, and just apply heat to it, it takes the shape that we trained it in the first place.
We also tested the deterioration of the Filoflex. One of the use cases that we anticipate happening with this device is that the child is going to be putting the device in their mouth, as babies do, and the outer interface of Filoflex will be interacting with the child's saliva. And so we tested the loss of mass in 3 unprinted Filoflex samples before and after submerging them in saliva over a 5.5-day period. The 5.5 days was an estimate of about 1.5 hours per day, which is meant to overshoot how long that Filoflex is actually going to be in the child's mouth over the product life of 90 days. And here you can see a bit of that testing and the data that came along with it. In the results, we found that there was around 0.5% material loss over the 5.5-day period, which is well under the standard. Also, Filoflex is known to be non-toxic and showed that you're able to ingest 5,000 milligrams or 5 grams per kilogram of weight, as was tested with rats. We also, like the previous group, used SolidWorks for the 3D modeling. With the previous group, they were able to make a somewhat lifelike looking hand. One of the problems was that it was more dimensioned to resemble an adult hand, we found, with longer, skinnier fingers. And also it had a large amount of notches cut into the fingers, which didn't appear too lifelike. So with our design, we used SolidWorks to make a hand that was more dimensioned to a baby's hand, as far as having a chubbier, fatter palm, shorter, stubbier fingers, and we also used less finger notches in order to make it appear a bit more lifelike. You'll also notice that with the previous hand, the thumb is oriented forward in order to enable grasping. With our hand, after some design changes that came along with the 3D printing, we decided to mainly focus on the load-bearing properties of the hand, which are meant for helping the child to sit up, crawl, position themselves. And so we oriented the thumb flat, which also made it easier to insert the nickel titanium alloy wires, as Kevin mentioned earlier. As for the internal wire structure, the previous group used this U shape, and they inserted that as they were printing the hand horizontally. So halfway through they stopped, inserted the wires, and then printed the rest. So those wires are now inaccessible for future use if something were to happen to the outer Filoflex material. And also the load bearing of the wires was mainly focused at the fingers, not much support at the palm. With our design, we tried to resemble more of a skeletal structure with having the nickel titanium alloy wires coming from the wrist, where they're affixed to a nut in the hand and streaming up through the fingers, dispersing through the palm for improved load bearing, and also left the possibility open for if something were to happen to the outer Filoflex material, the wires could potentially be taken out and put into another hand, so you save a little bit of material there.
So we used the Prusa i3 for the printing process, and we found printing with Filoflex in general to be extremely challenging. It's a very rubbery material. It's not like common materials like PLA, which are hard after printing. It remains rubbery, and as such, you have to print extremely slowly, otherwise your printer jams, or you'll see like strings and other defects in the print. We ended up using a print temperature of 240 degrees Celsius, a print speed of 20 millimeters per second, and we used a speed of 120 millimeters for non-print moves to try to break up those little strands that would remain. The print time was approximately 3 hours, and we used 13,000 millimeters cubed of our filament. After some consideration, we decided to print vertically. Horizontally was what the previous team used, and it has some benefits because in terms of structural integrity, but we weren't able to get a very clean looking print, and there were often strands and features that were not formed properly versus vertical. You can see some of our samples here. All the way to the left, we had some cylinders that we printed early on, and then a couple of horizontal prints that we had tried, and then the process kept going on until we finally were able to get a clean print for our funnel. For transformation testing, we wanted to test the ability for our nickel titanium wires to flex within the printed VeloFlex cylinders, and some of the variables we picked for this were different levels of infill. You can see here 80% infill, it's almost completely filled, and as you go up, you have more air gaps within the actual print. Layer height primarily is related to accuracy, and especially with VeloFlex because it's so rubbery, and as you extrude it from the printer, it tends to go everywhere, and you can't really get super high accuracy. It'll print far better at a layer height of 0.2 or 0.3 millimeters than it will at 0.1. So we primarily wanted to test the shape memory capability of our nickel titanium wire within the cylinders. And as you can see in the results, 10% infill provided the best flexibility for our actual hand and also provided adequate strength. We found the shape memory effect extremely difficult to utilize in this in our design for the 3-month-old infant. We had chosen a 0.03 inch diameter wire as it was, we had calculated that as our intended diameter early on, and that was also easily purchasable from Amazon, so we had gone with that. But it ended up not being able to adequately counteract the elasticity of our printed material. Additionally, the insulative properties of VeloFlex block exterior heat transfer. You can't, for example, use a hair dryer to just blow on the hand and heat it up. You could put it in boiling water to restore the shape. And also for our print, the digit size of the 3-month-old prevents or poses difficulties with the wire diameter as if you make it too wide, it'll actually just start to impede the structural integrity of those fingers. So there is potential for hands that are designed for children older, like maybe 6 months or so, but for a 3-month infant, this was about what we could do as far as bending. For our tensile test, we picked 2 standards, ASTM D412 and 16 CFR 1500.53, and these were intended for testing abusive toys and other articles intended for use by children over 36 but not 96 months of age. The pass criteria for this was simply to withstand 15 pounds for 10 seconds. And our setup was essentially clamping the hand only at the fingers, and then we attached them and this was actually about 25 pounds. And including the base plate, it was a total of this is 26 pounds. But essentially, it did pass the test. The previous team used the Canadian standard, which tested this for 10 minutes, and we tried to be a little ambitious and do that. And the hand survived, but unfortunately, the nut didn't really cure properly, and it failed from there. But it did pass the intended standards we set for it.
So compression test we did is to validate the purpose of the purpose of this to bear weight, to crawl, and to sit, and to push and pulling, to stand. So we follow 16 CFR standard as it was with the tensile test. And the pass criteria we got from the standard, it was the hand withstand 30 plus minus 0.5 pounds per 10 seconds. So we did the test using the scale. We push it all the way to down, and it actually over 40-50, but we got the picture of 31.5 pounds per 10 seconds test pass. So it validates that the hand can support a baby to their weight. So for cost analysis, we used all the material. It was $11.46 compared to previous team. They used $7.91. You might ask, why is it more expensive? But if you see the graph there, if you keep using it, because the previous team's durability was really low compared to ours. So when you keep using it, the previous team's design will keep replacing while we continue to use. So our design is more cost effective compared to the previous team, and other cosmetic arm costs over $3,000 to $5,000.
All right, so conclusion.